Okay, so thank you all for joining the joint Israeli probability seminar. And today we're very happy to have Dor Elboim from Princeton University to tell us about coalescence of geodesics and the BKS midpoint problem in first passage percolation.
Okay, thank you very much, Ron, and thank you all for coming. Yes, so today I'm going to talk about first passage percolation, and this is a joint work with Barbara Dembin and Ron Peled. Okay, so first of all, we are going to define the model of first passage percolation. I guess most of you know it already, but we'll define it. Okay, so you have the graph z squared, and the edges are between nearest neighbors in the grid. And yeah, and you can do it on any graph, but throughout this talk, we will concentrate, throughout the talk, we will concentrate on z squared. Now, for each one of the edges of the grid, you sample an independent random variable, the weight of the edge, WE, a non-negative weight. And all of these edge weights are IIDs, independent and identically distributed according to some distribution F. Okay, and now you define a random metric on the set of vertices. So the distance between 2 points, or the passage time between X and Y, is defined as follows. So it's going to be the minimum over all paths connecting X and Y of the passage time of the path. What is the passage time of the path? It's just the sum of weights along the edges of the path. So you are trying to find the path such that the sum of edges along the path is minimal. Okay, so once again, you have here the grid. On each one of the edges, you have this random weight independent of all other edges. And then you have 2 points, let's say 0, 0, and n0. And you want to find the minimal path from 0, 0 to n0, minimal in the sense that the sum of weights along the edges is minimal. Okay, you can maybe, by the way, this minimal path is called the geodesic, and the weight of the path is the passage time between the points. You can maybe think about it as a network of roads, and each one of the little roads, you wait some random amount of time due to traffic, let's say, and then you have the ways up, and the app knows all of these random weights, and then it gives you the optimal path that you should follow. Right. Okay, so you take, let Tn be the passage time from 0, 0 to n0. Perhaps not very surprisingly, this passage time grows linearly in the distance between the endpoints. And it's not very hard to show that if you divide the passage time by n, it converges to some constant, deterministic constant, which is called the time constant. You can do it using Fekete lemma, for example, or subadditivity.
When you say grows, you mean the expectation grows, right?
The passage time itself grows linearly. If you take that,
it's a variable. So when you say it grows, you mean.
Sorry, I couldn't. Is it a problem with my internet connection?
No, mine.
Yes, I mean that if you divide it by n, it converges to some constant in probability, let's say, or actually almost surely. So this is not very hard to show. And it is conjectured that the variance of the passage time is of order n to the 2/3. So that fluctuations are of order n to the 1/3. Note that it's less than the fluctuations of some of n independent variables. So the passage time is less noisy than a sum of independent variables. Also, it is conjectured that the transversal fluctuations are of order n to the 2/3. What do I mean by that? So when it turns out that when you zoom out you take two very far away points, you zoom out, what you see, it is conjectured to be just a straight line. But when you zoom back in, you can ask what is the distance between this geodesic and the straight line connecting the points. And it is conjectured that this distance is of order n to the 2/3. Right, so yeah, in first passage percolation, usually you always ask asymptotic questions as the 2 points get really far. And you're also interested in the geometry of these geodesics. And yeah, then you ask yourself, where do all these conjectures come from? And so this model is conjectured to belong to the so-called KPZ universality class. And in this class, some of the models are so-called exactly solvable or integrable. And in these exactly solvable model, you can compute everything that you want and you can prove all these conjectures. Maybe you know some of these models, for example, the longest increasing subsequence of a random permutation, or exponential or geometric last passage percolation, or Poissonian last passage percolation. But any first passage percolation model is not in this integrable, is not one of these integrable models. Okay, so before going to our results, I want to review this limit shape theorem. This is a theorem of Cox and Duret, and it says the following. So you define the ball of radius t. This is just the set of vertices with distance at most t to the origin. And the theorem says the following. So it says that you have some deterministic convex body, B, which depends on the edge distribution F, such that with probability 1, if you take this random ball and you rescale it by t, then it's going to be, for sufficiently large t, it's going to contain in 1 plus epsilon times b and 1 minus epsilon times b. Yeah, so here is a simulation. So this is a simulation of C-Tang, and it's taken out of a very nice survey called 50 Years of First Passage Percolation. So in here you take edge weights, which are exponential 1, distributed according to exponential 1 distribution. And then you see this random ball growing. So this is for t equal to 0, t 70, 135, and 250. And you really see that this random ball converges to some deterministic shape. Yeah, so this limit shape is conjectured to be differentiable and strictly convex, but all of these questions are open. You don't know a lot about this limit shape. So what does it tell you, this limit shape theorem? It basically tells you that if you take this metric space, you take a grid of n by n, and you take the random metric space of passage times, and then you rescale everything by n, you basically get a limiting deterministic metric. And this deterministic metric is in fact a norm, and the unit ball of the norm is the limit shape. So more or less, it tells you that if you want to compute the main order of passage times, it only depends on the direction that you are going. And then the limit shape exactly tells you how expensive it is to go in any different direction. Okay, this is the limit shape theorem. Now we can go to our main results. You take gamma h to be the geodesic from 0h to nh. By the way, under some mild assumption on the edges, this geodesic exists and is unique. For example, if you assume, throughout the talk, we will assume that the edge weights have an absolutely continuous distribution. And in that case, the geodesics exist and are unique. And yeah, so this is the geodesic gamma 0 from 0, 0 to n0. And this is the geodesic gamma h from 0h to nh. And it turns out that what you will see is that these two geodesics coalesce. What do I mean by that? They intersect and proceed together for almost the entire way. Yeah, so if we go back to the analogy with the roads, then you can maybe think of it as as a certain highways that are created, so that it doesn't really matter where exactly you're coming from, and it doesn't really matter where exactly you're going to, you will always use these highways. Okay, but so here is the main theorem. First of all, the assumptions. So you take F, this is the edge distribution, and you assume that it's absolutely continuous, has exponential tails, and also you assume that the limit shape corresponding to the distribution is not a polygon with less than 40 sides. So yeah, remember I told you that
assumption, I assume it's conjectured to be true in any case, but you need to assume it because the conjecture isn't proven, right?
Right, that's true. That's exactly right. So as you remember, I told you that this limit shape is conjectured to be differentiable. So if it's differentiable, it shouldn't be a polygon, but if it's not a polygon, it's fine. But even if it's a polygon and it has more than 40 sides, it's also fine. And in fact, later in the talk, we will give, our third result will be that some explicit family of distributions satisfy this assumption. This assumption is so weak that you can actually prove it for a certain explicit family of distributions. Okay, this is the assumption. And now what is the theorem? You take n sufficiently large, and you take, this is the length of the geodesics, or the distance between the endpoints. You take the vertical distance h to be of order n to the 1/8. And then you get it with high probability, the symmetric difference between the two geodesics. This is the set of edges that belong only to one of the geodesics, is of order little o of n. Which means that you only have some negligible amount of edges that don't belong to the intersection between the geodesics. Right, so
no explicit bounds on the little o. I mean, what sort of order
okay,
of
very
magnitude?
good. Yeah, yeah. So as you say, if you take h to be like n to the slightly less than n to the 1/8, n to the 1/8 minus epsilon. In this case, as you said, the little o of n will be upgraded to polynomially less than n. Let's say n to the 1 minus delta. And also this high probability will not only tend to 1, it will be polynomially high probability, like 1 minus n to the minus delta. Right, and it will be very interesting to upgrade this exponent 1/8 to something bigger. It should be. Can you mute there is a...
Yeah, I have a question. That's why I'm not muted. Sorry about that. Is it important that the points are on the boundary of the square?
No, actually, this is a bad picture probably, because no, you don't assume. Actually, if they have to stay inside the slab, then you don't need this assumption. But no, this theorem holds for two. The geodesic doesn't have to stay inside this slab. It's a bad picture.
Can you flex it to take points which are not in that particular direction? I mean, you have a...
Yeah, you are always asking questions that I'm right about to. Yes, exactly. So this theorem doesn't really hold only for horizontal geodesics. It holds for any geodesics in any direction, as long as they are long enough and not too far away from each other. Right. Okay, I guess that's it. This is the first result.
There is a question in the chat, Dor. I read it to you. Do you have a lower bound on the symmetric difference from Shang-Ji?
Yes, so yeah, as I said, if you take h to be, let's say, n to the 1/8 minus epsilon, then the symmetric difference is going to be of order n to the 1 minus delta, like polynomially less than n.
The question is on a lower bound. Can it...
Oh, excuse me, a lower bound. Yes, you can get, of course, some, like, it's lower bounded by the distance, h. You can probably do something better than that. I won't get into that. Okay, let me show you some simulations. So here we simulated it with a uniform 0-1 distribution. The length of the geodesics, or the distance, will be 2000, and the vertical distance between the geodesic is 30. So as you see, the two geodesics coalesce. Here is another picture. These are independent samples. This is an independent sample. And note that in here, we rescale the y-axis, so that if you don't rescale, you just see two straight lines. But when you rescale a little bit the y-axis, you get some interesting pictures. Here's another one. You simulate it with the Dijkstra algorithm. Right, here is another one. So in here, it didn't work. But yeah, this is in some sense compatible with our results, because they coalesce only with polynomially high probability. And so sometimes it doesn't happen. And also in our proof, we show that in some sense, when the two geodesics are close, they will coalesce with exponentially high probability. So that on the event that they didn't coalesce, it's very likely that this is the picture that you will see, that the two geodesic will be far away from each other. Okay, good. Let's move on to the next result. The next result is the BKS midpoint problem. So what is that? Recall that Tn is the passage time from 0, 0 to n0. And there is a very famous result of Itai Binamini, Gil Kalai, and Oded Shram that states that the variance gives a sublinear bound on the variance. Remember, it is conjecture to be of order n to the 2/3, but this is some sublinear bound. And the way they did it is using the theory of Boolean functions. And in particular, they use Talagrand's influence inequality. Right, so this inequality bounds the variance using the influence of the edges. What is the influence of edge? It's just the probability that when you increase slightly the weight of the edge, it will increase the total passage time. Or in other words, this is the probability that the geodesic will pass through a specific edge. So in order to use this Talagrand inequality, you need to give bound on the probability that the geodesic will pass through a specific edge. And in their paper, they were not able to do it, but they used a certain averaging trick. So it turns out you can go around it. But still you have this very interesting problem, which is show that the probability to pass through a specific edge decays. It sounds easy. All right, so let's make this problem more precise. You take gamma n to be the geodesic from -n0 to n0. And the BKS midpoint problem is to show that the probability that the origin, the midpoint, is in the geodesic tends to 0. Yeah, so it sounds easy, but it was open for some time. It was then solved non-quantitatively by Alberg and Hoffman, and before that by Hanson and Damron, with some assumptions. But both of these results, they hold in the general setting in which the edge weights are stationary and not independent. And in this setting, you probably cannot get any quantitative bound. You probably can only get like arbitrarily slow convergence of this probability. But here is our theorem. So you assume the same assumptions: continuous exponential tails, and not a polygon with less than 40 sides. Under these assumptions, you get this polynomial bound. So this is the first polynomial or quantitative bound on this probability. Right. So a couple of comments.
There is a question in the chat. Is it of order n to the minus 1/3? Is that
Right? So no, this exponent is far from optimal indeed, but it should be of order n to the minus 2/3. Because remember, the transversal fluctuation, like how much you are far from the straight line, is n to the 2/3. So you sort of assume that it's uniform in an interval of n to the 2/3. Right. So this is far from optimal. Okay. Yeah. Now I want to explain why these two results are related, and in particular why this BKS midpoint follows from the coalescence. So why is that? So you want to show that the geodesic between these two endpoints, the probability that it passes through the midpoint decay. So by translation invariance, this is exactly like the probability that the geodesic between these two endpoints will pass through the corresponding midpoint. And the same for any other two on the line. Now, by the coalescence result, we know that all of these geodesics will coalesce. We know that any two of them will coalesce, and therefore all of them will coalesce. And now you only have one geodesic, so it will intersect the middle line at some point, which means that all of these events, that these two passes through the midpoint and these two passes through the midpoint, all of these events are disjoint, and they have the same probability by translation invariance, which means that the probability is small. All of these events are disjoint and have the same probability, so the probability is small. But actually, they are not disjoint, because maybe the geodesic passes through more than one point on the middle line. Maybe it's as bad as passing through all of the points on the middle line. But no, you can rule out something like that. And in fact, you can also use a shortcut and do the same with a square of endpoints, and then a square of midpoints. And now it's completely clear that one geodesic cannot cover the entire square.
Excuse me, when you say rule out,
yes,
I doubt he can hear. When you say rule out, you mean it's very low probability, right?
Yes, exactly. And actually, the argument for ruling it out is not so simple, but using this new argument with a square, it's simpler to do it. Because it's very clear that one geodesic cannot cover an entire square. It will just be too long in some sense. Okay, so once you have coalescence, you have the BKS midpoint. It's not very hard to do the midpoint with the coalescence. Okay, now for the last result. So this is the limit shape result. In here, we are going to verify that some explicit family of distribution satisfy the limit shape assumption. So here's the theorem. You take X, which is a random variable supported on 0, 1, and you take epsilon sufficiently small. Then your distribution, your edge distribution, will be 1 plus epsilon X. So this is like a small perturbation of the constant weights. And then you take B epsilon to build the limit shape. And then it shouldn't be a polygon, but what we can show is that if it's a polygon, it has at least log 1 over epsilon over log 1 over epsilon sides. So in particular, if epsilon is sufficiently small, you have at least 40 sides. Yeah, a simple corollary is that you can basically multiply all edge weights by a constant factor and not change anything, not change the geodesic, only scale, it's only rescaling the limit shape. And therefore, you can multiply all edge weights by 1 over epsilon, and then you get a distribution of the form m plus x. X is a constant variable, and m is sufficiently large. And then you also get a lot of sides to the limit shape. So for example, if you take the uniform distribution between m and m plus 1 for m sufficiently large, let's say m equal to 100, then you should have at least 40 sides, and then all of the theorems on the coalescence and BKS, they hold for this distribution. Okay, let me mention some previous results. in the exactly solvable, you have very accurate information about coalescence of geodesics. So in there, it is known that geodesics at distance n to the 2/3 will coalesce. We have only n to the 1/8 in first passage, but in the exactly solvable model, you have much better exponent. So there is a sequence of works, first proving upper bound and then lower bound. And actually, you have extremely accurate information, you know. So you take geodesics at distance c times n to the 2/3, and you can exactly estimate the probability of coalescence as this constant c tends to infinity or tends to 0. Okay, but nothing like that is known in any first passage percolation model. And in first passage percolation, you only have, like before our result, you only had like limited and non-quantitative results. So under some assumption, you can prove that two infinite geodesics will coalesce. So it doesn't give you a quantitative distance in which they coalesce. And as I mentioned, you also have a non-quantitative BKS midpoint with some assumption and then without any assumptions. Okay, that's it. Yeah, are there questions up to here?
I want to add.
Sorry, I cannot hear you.
Yeah, we cannot hear you. Could you say again? Maybe you can write in the chat the question.
Okay, we'll get back to it. We'll have some time for questions in the end. Okay, so let's talk about the proofs. Yeah, so we already proved the BKS using coalescence. We are not going to talk about the proof of the limit shape result. We just want to prove the coalescence.
Dor, there is a question in the chat now. What is exactly solvable in this context?
Right, so the exactly solvable models are, for example, exponential last passage percolation or geometric last passage percolation. You have like 3 or 4 exactly solvable models, and none of them are first passage percolation, but they are conjectured to be in the same universality class. And this is where all the conjectures on first passage percolation come from. Okay. Yeah, so we want to prove the coalescence. For simplicity, we are just going to assume that the distribution, the edge distribution, is supported on 0, 1. So all of the edge weights are between 0 and 1. Recall that Tn is the passage time from 0, 0 to n0. Gamma 0 is the geodesic from 0, 0 to n0. And gamma h is the geodesic from 0h to nh. It's the upper geodesic. And so the first thing that I want you to note is that it suffices to prove that the geodesics intersect. And why is that? Because if you have some argument like that, then you can apply it once here in the beginning of the interval, let's say in an interval of length n to the 1 minus epsilon, and also in the end of the interval, again on an interval of length n to the 1 minus epsilon. And then if the two geodesics intersect in here and in there, it means that the geodesics are unique, so they really have to proceed together for the entire way. So really the difficulty here is to show that the geodesics intersect. So let's show it. And we are going, throughout the proof, we are going to assume that the variance, remember the conjectured variance is of order n to the 2/3. So it's much easier to do the proof with this assumption. In the end, I will say a few words about how to remove this assumption. Okay, and we will prove it for a vertical distance of order n to the 1/10. You can then try to optimize the exponents you get. Yeah, and okay, let's start the proof. So the first definition is the definition of R tube. So for R larger than 0, you define the R tube around the path P. This will just be the set of vertices, a distance at most R from the path P. So the R neighborhood of the path. Okay, good. Now here's the main idea. You take h to be n to the 1 over 10, r to be slightly larger, n to the 1 over 9. And you prove the following two lemmas. So you will have lemma 1 and lemma 2. So let's try to understand lemma 1. Lemma 1 says the following. It says that with high probability, any path q from 0h to nh that spends at least half of the time in the R tube around the lower geodesic, around gamma 0, and is disjoint from gamma 0, has a large passage time. Okay, so any path like that. By the way, the red is the lower geodesic, the green here is the tube around the geodesic, and the blue is the any path, is any path that spends at least half of the time. So think about it like that. Any path that is both close and disjoint from the lower geodesic has large passage time. And what is large? Large, it means larger than the passage time of the lower geodesic plus 3h. This is lemma 1, a bit technical. I hope you followed. Yeah, so here is lemma 2. Lemma 2 is that with high probability, the upper geodesic spends at least half of the time in the R tube around the lower geodesic. So lemma 1 tells you that any path which is both close and disjoint has a large passage time. Lemma 2 says that the two geodesics are close. Do you see why these two lemma implies that the two geodesics have to intersect? Here is the explanation. Suppose otherwise. Suppose that they are disjoint. If they are disjoint, by the second lemma, they are close. By the first lemma, anything which is both close and disjoint has large passage time, which means that the upper geodesic has large passage time. But this is a contradiction. Do you see why? You cannot have that the upper geodesic has a much larger passage time than the lower geodesic, plus 3h, right? Because here is a shorter path. I'm going to show you a shorter path, but gamma h is a geodesic. So here is the path. You just go from 0h down to 0, 0, then proceed with the lower geodesic, then go up again to nh. The passage time of the new path is at most h, because the weights are bounded by 1, plus the passage time of the lower geodesic, plus h. So it's shorter than the passage time of the upper geodesic. This is a contradiction. Right, so is that clear? Once you have the two lemmas, you are done. So now it just suffices to prove these two lemmas. Let's start with the second lemma because it's much easier. So here is the proof of lemma 2. You want to show that the two geodesics are close. So this is the lower geodesic, this is the upper geodesic. You define f0 of x to be the height of the lower geodesic above x. So the height of this point. And similarly, fhx is the height of this point. Now, by symmetry, you have that the expectation of f0 is 0 because you can just reflect the geodesic. And similarly, the expectation of fhx is h. Now, the second observation is that fh of x is always larger than f0 of x, right? Because either they coalesce or the upper geodesic goes above, right? It's not like the upper geodesic can go below and then back up because then they will just coalesce. Which means that the height of this point is always more than the height of this point. So now you have this random variable, which is positive, and its expectation is h. And therefore, by Markov inequality, the probability that it's larger than r is at most the expectation over r. And r is much larger, so it tends to 0. Right, it's a very simple and easy proof, but there is something wrong in the proof, right? Did you notice it? What is wrong in this proof? It's this part. Because maybe the upper geodesic circles the lower geodesic like that. Yeah, and this is a pretty unfortunate problem, and we were stuck on this problem for some time, and eventually we could only solve it. You want to rule out this picture basically, and we could only rule it out using some limit shape assumptions. So in particular, if you don't have this problem, if you work in some directed version where the geodesic can only go forward, in this case, you don't need any assumptions. Right, if I'll have time in the end, I will explain why how using the limit shape assumptions, you can rule out this picture. But anyway, let's move on to the main lemma, which is lemma 1. So what do you have here in lemma 1? Once again, you want to show that with high probability, any path which is both close and disjoint to the lower geodesic has large passage time. Okay. So let's say I want you to remember one more notation. So for a path P, it can either be a random path or a deterministic path. You define QP to be exactly the set of paths which are both close, spends at least half of the time in the R tube, and are disjoint from P. This is QP. And yeah, the second thing that I want to do is to replace, so here you say that the passage time of all the paths are long. Passage time of the path is just the sum of weights along the path. But you have here a random benchmark, and I want to make it a deterministic benchmark. So this is just the passage time. You can bound it using the variance assumption. So the passage time of the lower geodesic is Tn. The variance is bounded by n to the 2/3 by the assumption. And therefore, you can bound this this random benchmark just by the expectation plus n to the 2/5. 2/5 is just some random exponent, which is larger than 1/3, because the fluctuation are of order 1/3. Okay, so you basically lemma 1 follows from this lemma 1 prime. We did nothing so far. So we want to show that with high probability, any path which is both close and disjoint to the lower geodesic has large passage time. Now here is the first actual step, which is going to be to replace this random geodesic with a deterministic path. Okay, so I claim that lemma 1 prime follows from the following claim. It suffices to prove that for any fixed path, now the path P is fixed, you want to show that for any path Q which is both close and disjoint, it has large passage time. Now, do you see why lemma 1 prime follows from the claim? Suppose you prove the claim for any deterministic path P. Why it follows for the random path? Because you condition on the path, right? But it's not as easy as that, because like the event that this deterministic path is a geodesic depends on all of the weight, and so is this event. But it's FKG inequality. Right? This event just tells you a bunch of passage times are large, which means that, so you're going to condition on the edges along the deterministic path. And then this event is increasing in all of the other weights. You work in the space of all the other weights. You think of the weights on the path as constant. So this event is increasing, and the event that this path is a geodesic is also increasing in the weights outside of the path. If you increase the weights, then it's more likely that this path is a geodesic. So therefore, by FKG inequality, you exactly have that the probability that both of these events hold is larger than the product of the probabilities. In here, you also use that this event is independent of the weights along the path, right? To say that the conditional probability is like the actual probability. Okay, that's it, right? If you sum both sides over all the paths P, you get on the left-hand side the event in lemma 1 prime, and in the right-hand side the event on the claim. So now you really have to just prove this very simple claim. You have a deterministic path P. you want to show that any path Q, which is both close and disjoint from the path P, has a large passage time. Okay, let's prove it. Here's the first step. So for any path Q, you have that the passage time of the path, the sum of weights along the path, is at least the passage time between these 2 points minus 2h. Right? It's the same trick, right? Because this path, the path that goes up along Q and then back down, is a path between 0, 0 and n0, and therefore it's larger than its weight is larger than the passage time. And now you are going to use the assumption on the variance once again. So this passage time is bounded by the expectation minus n to the 2 over 5. Because the fluctuation are of order n to the 1/3. And h is negligible, h is much smaller. Right, but this is not good enough, right? So here you want to prove this claim with a plus, but you prove the lower bound with a minus. So what are you going to do? You are going to increase the weights. So it sounds a little bit like cheating, right? You increase the weights, you get something completely different. But it turns out that if you just increase all the weights slightly, you basically didn't change anything. And now we are going to take a certain detour out of the proof, and we are going to talk about the technique of Mermin-Wagner type argument. Yeah, so here's the claim. Now it's completely independent of the proof. Yeah, you have x1 up to xn. These are IID random variables. And then you add to each one of the variable 1 over root n, where n is the number of variables. And you have this vector of x's and this vector of y's. And the claim tells you that the total variation distance between these two vectors is at most 1/4. Which means that if you add to each one of the variable just slightly, you basically cannot distinguish between this set of vectors and the other set of vectors, the other set of variables. Right, and actually this claim is false, but let me prove it when xi is normally distributed. So in this case, it is correct. Yeah, so how do you prove this claim? Xi are normally distributed, and therefore the vector x is spherically symmetric, which means that adding the vector 1 over root n, 1 over root n, 1 over root n is exactly like adding the vector 1, 0, 0, 0, because you can just rotate one vector to the other. Which means that the total variation distance between x and y is like the total variation between just taking one normal random variable and adding 1 to it, which is at most 1/4. Right? It's very simple. Yeah, and as I said, this claim is wrong in general, and you basically cannot add, you need to add it with a certain bump function. I won't have time to get into the details of that. Yeah, but for now, just assume that this claim is correct. That once you have n random variables, you can just add to all of them 1 over root n, and you cannot distinguish between the. Yeah, by the way, if you add slightly less, let's say n to the minus 1/2 minus epsilon, then the total variation will already tend to 0. So now you completely cannot distinguish between the two sets. Okay, now back to the proof. What you are going to do is the following. You are going to increase the weights of all of the edges inside this tube. Okay, you define a new environment. So W is the old environment. You define a new environment, which is just the old environment plus n to the minus 4 over 7. This is for all edges in the tube. And then you just take the old environment outside of the tube. How many random variables do you have? You have n times r times the size of the tube, which is n to the 10 over 9. Yeah, now by the claim, you can basically add 1 over root the number of random variables. which means that you can add 1/root the number of random variables. So if you add this amount to each one of the variables, you basically didn't change anything. The new environment is completely like you cannot distinguish between the old environment and the new environment. Right, but so you didn't change anything, but you did change something, right? Because now passage time of paths is larger. So T prime Q is the passage time, is the sum of the new weights along the path. And TQ is the sum of old weights. So the sum of new weights is at most n⁻⁴/7 times the number of edges in the tube, which is at least n/2, because remember, we only consider paths that intersect the cube, that spends at least half of the time inside the tube. So now this amount is exactly enough to make this minus into a plus. Right. Yes, so what did we get? We get that the probability that this event, the probability that any path is, the passage time of any path is larger than the deterministic bound with a minus. If this event holds, then in the new environment, you have the improved bound with a plus instead of a minus. But we know that the total variation between the new and the old environment tends to 0, which means that any event that holds in the new environment also holds in the old environment with almost the same probability. So that's it, you get your claim. Yeah, this is the end of the proof of coalescence using this assumption of n to the 2/3. Yeah, and I don't really have, like, when you don't have this assumption, everything becomes exponentially more complicated, and I won't have a lot of time to talk about that. Maybe I will just say the idea that what you need to do is split into a lot of small intervals. And then what you say, so how did you use the variance assumption? You said that the total passage time of the path cannot be too much larger than its expectation. But when you split it into a lot of small intervals, you can say that on one of these intervals, the passage time is not too large, because if it was larger on all of them, in some sense, it would be too large on the total. The total passage time will be too large. Yeah, I won't have time to give the details of this. Basically, you apply the same strategy, but just on one of these intervals. Yeah, I think I have a couple of more minutes to maybe explain the idea behind this issue, like how using the limit shape assumptions, you can rule out this issue.
Dor, there was an earlier question in the chat about the variables being normally distributed with variance 1. Maybe if you make this assumption.
Yes, you're completely right. Yeah, we need the random variable to be constant, like not too small variance. Yes.
The question was about whether they're Gaussian, the random variables, because you mentioned that, I guess.
Yes, and Gaussian, yes, normal Gaussian. It's But the claim, you have some version of the claim that holds for any weights. Okay, let's move on to rule out this picture. So it makes sense that you want to rule out this using something on the limit shape, because the limit shape tells you how expensive it is to go in any direction. And in some sense, in order for something like that to happen, you need to go in the wrong direction for a long time. Okay, let's try to explain this. So here's the first claim. The claim says that with high probability, the geodesic from here to here doesn't contain a point of the form 0y for y larger than √n. So this is not good enough to rule out this picture, because our geodesics are a distance n to the 1/8. But it's a step in the right direction. So how do you do that? It's very simple. You define this passage time. You take T1 will be the passage time from 0, 0 to 0y. T2 is the passage time from 0y to n0. And T3 is this passage time. And now the proof goes as follows. one can show that with high probability, so the passage time, this passage time that goes diagonally cannot be much shorter than the passage time that goes straight. And also the passage time T1 cannot be less than a constant times y. And y is larger than root n, right? Which means that with high probability, T1 plus T2 is strictly larger than T3. This is what you show. But on the event that the geodesic passes through this point, T1 plus T2 is equal to T3. And in fact, you can show that something like that holds with extremely high probability, so that even if you union bound over the points y, you still get the result. Okay, now the second claim, it's just a proof by a picture. So the second claim is that you cannot go, so a geodesic from 0, 0 to n0 cannot go to minus x0, cannot pass through a point minus x0 for x larger than n to the 1/4. Now you are getting close to what you need. You need n to the 1/8. So it's already closer. Do you see how to prove this claim using the first claim? It's very simple. You consider this point of intersection with the y-axis, 0y. So now by the first claim, y has to be less than root n. It cannot be larger than root n. And then you can basically forget about this point. You can just consider these 3 points, rotate the entire picture by 90 degrees. And you have here a point at distance less than root n, which means that you cannot go in this direction for distance more than root of root n, which is n to the 1/4. Yeah, and so once you have this, you sort of ask yourself, what is so special about these directions? That the geodesic from here to here cannot go for root n in this direction and cannot go for n to the 1/4 in this direction. And when you think about it a little bit, why can't you do it on these 3 directions? Why can't you do the same argument and say that the geodesic from here to here cannot go root n in here and then n to the 1/4 in here? Yeah, and when you think about it, you realize that the assumption that you need is that exactly the directions are not on the same flat edge of the limit shape. So sort of, this is the limit shape, and the geodesic from here to here can go for pretty long in this direction, for a linear amount of time in this direction. But it can only go for root n amount of time in this direction. And it can only go n to the 1/4 in this direction. Because the limit shape sort of tells you how expensive it is to go in any direction. All right, so if you assume that your limit shape has enough sides, then you can basically repeat this argument again and again and get all the way to where you want to be, like n to the 1/8. Okay, yeah, that's it. Questions?
Thank you, Dor, very much. And any questions? You may unmute yourselves and ask.
I have a question. Do you have any kind of bounds, lower bounds, I guess, for the probability that they do not coalesce? Or upper bounds for that? I mean, that's the small probability.
Yes. So I guess you can lower bound it by 1/n or something, because somehow you have this translation invariance and they cannot coalesce like a distance at linear distance. So sort of the picture that you will see is that you take all these points on the line and then some of them will coalesce, and then at some point it will stop coalesce and it will sort of form a new, I guess it's hard to explain, but I guess it's not very hard to get like 1/n or something like that. Yeah, somehow by translation invariance.
Okay, thanks.
There is a question from the chat from Sarai Hernandez Torres. She asks whether if your assumptions over h are weaker, say h is less than n to the 1/4, then the number of sides of the polygon would be smaller.
But it's not a, okay, yes, so we don't know how to prove it for h, which is n to the 1/4. We can only do it for very small h. Just if the two geodesics are very close to each other, then we can show that they coalesce.
Thank you. Yes, I got the wrong number. Let's say instead of 1/8, 1/32.
Yeah, you can. Yeah, but you still need something. It's not like we can show without any assumptions.
But I mean, so you say 40 sides of the polygon. Can you show it for 20 sides?
20? I don't know. I need to do the computation. Maybe like it's possible. Yes.
Maybe my question is that is this just a direct relation between the sides of the polygon and this restriction on how many, on how close is H? Or is there something else that you're using? This
yeah, in some sense, as long as
shape?
H, yeah. So the assumption is only to rule out this picture, right? So in some sense, as long as H is smaller, it's harder to rule out the picture because then you have to travel for a shorter distance. So it's not like as long as H is smaller, you can get better and better, like weaker and weaker assumption on the limit shape. It's not, yeah, I would say it's not, yeah.
Well, thank you.
Thank you.
So I have a question about this picture, this bad event. I don't understand something about it. So here what you say, the good event was when you stayed above the blue line all the time.
Yeah.
And you also demanded that you are not too far away most of the time? Because I don't understand.
Yeah, it sort of follows, like if you know that this event has exponentially small probability, then we have the Markov, we have this proof of lemma 2 that says that if this geodesic is above this geodesic, then they have to be close in some sense.
But what is the difference? In this bad event, then you know you cannot pass from above to below a lot of times, at least not what I'm, if at the bulk of the left-right crossing, you cannot pass from above to below all the time. No, so you stay below the blue line, and then I don't quite understand what is the difference between this and being above the line. If you could pass a lot of times, then that's a different picture a bit. That something seems implausible.
Yes, this is a very good question, and it's possible that you can. We were it's possible that we missed something, but basically, suppose you go below the lower geodesic, then you can, without the limit shape assumption, you can get pretty far. You can get up to a distance of root n down, and then it's sort of too far to run the argument that we have.
Well, maybe what is the difference between getting too far down to root n and getting up to root n? Just going instead of going below, going to the distance square root n above the blue line. Why is this?
It's a good question. It's possible that you can do something. It's possible that you can somehow do it without the assumptions. It's possible. We could not.
Gidi, we show that if you don't circle, if the red geodesic doesn't go below the blue geodesic, then it also doesn't go up to root n. But in order to show that it doesn't go up to root n, we need to know that it doesn't go below the blue geodesic because we use Markov's inequality for that.
Yeah, so it just confuses me why, as long as it cannot cross, so maybe my question is, maybe you can use the fact that you cannot cross above or below the blue line, on this interval that the blue line spans, and can only cross above and below by going far away, to show that you are either most of the time above it or below it, and then use the Markov just from that side. I don't quite understand the. Okay, I'm not sure exactly how I offer to proceed here. But.
Yeah, it's worth thinking about it. Like, if we can do it without the assumption, it will be really cool. Like, and we are not sure that it's impossible.
You can be like if when you are above, if we know that with high probability you stay above, then we can prove that this probability is below that the fact that we can have the coalescence. But if we have like positive probability to go above and below, then it's possible that when it's go above, it's go very above, and when it go below, it go very below, and then we cannot prove the coalescence in that case. But we can exclude that if the probability to go below to circle is really small, but not if it's some constants. So I don't know if that answers.
Yes, thank you. I see why it's the same kind of problem now. So if you go far away above them, you will also go below with a relatively smaller descent.
Yeah.
Okay, thank you.
More questions to Dor? Okay, if not, let us thank Dor again for a very nice talk.
Sorry, can you